How do y'all feel about solving with
Pretty all right.
Gaussian elimination? You're good? Okay. Remember on your test, if I ask you to solve, I'm not just looking for an answer. I'm looking for a process. So if you use all kinds of weird eliminations, I think I told my other class, but maybe not you guys, I will literally say on your test, I will give you a problem and I'll say write your answer in, in ax plus by plus cz equals, not write your answer, but show me how you go from your equations to, and I'll give you something like this. I'll say give it to this form and then use back substitution to solve. So I realize there might be another way to do it. Like you can use Gaussian elimination to solve different ways. Like I could make these three values zeros and solve for x first. But I'm going to want you to do it this way. For one, it makes it a whole lot easier for me to grade your work because your work will always look similar to mine, right? So even if your answer's wrong, I'll be able to look at it and be able to find your errors and grade you appropriately. But I'm going to ask you to go to that form. So if all you do is have an answer and you're not in that form, you're probably going to lose most of all of your credit for that particular problem. Y'all with me on that? All right. So today, we're going to be looking at something called partial fraction decomposition. And believe it or not, you actually did a little bit of this last year. You didn't actually do the decomposing part, but you actually were solving for a couple of the variables early in Algebra 2. Well, if you were with me, early in Algebra 2. And it's actually a very common little math team question to be able to, once you get it partially decomposed, to be able to solve and figure out these variables I'll be describing to you. But to give you a hint of where we're going with this, and by the way, if you're one of those who's like, yeah, I think I'm going to take BC next year, and we'll talk more about that in the next couple of months, because honestly, probably most of you could take BC. The question is, would you thrive in BC? So what I want to describe to you guys, and maybe a month or so right before registration, is the difference between the two courses. I don't think you should take BC personally unless you've got a fighting shot of getting an A there, because it makes no sense to get a C in BC and have your head spinning all year, right? And then you don't have a good calculus foundation. Even if you manage to eat by and pass the AP test or whatever, it makes no sense to me to have a loose, not so great ability to do calculus and then march off into engineering or whatever, and then you have to take Cal 3 and differential equations, and you're screwed. Okay, and we've seen that before. Or take BC and not pass the test, and then you have to go back and take Cal 1 and Cal 2 again. Makes no sense to me. So I will advise you and tell you what I think and describe to you the kind of student I think that should take it. But AB, for the most part, is a very doable course. Most people who have C's in here make high B's or A's for me in AB. It's easier than this course, in my opinion. It requires less work on you if you pay attention in class. Smart people like you tend to do really well in an AB course. The BC is not really harder. It's just more. But it's kind of like walking 26.2 miles over the course of a week is not that big of a deal. But doing 26.2 miles in a 4-hour period is a big deal, right? So it's not like the distance is, the content in BC is that much more difficult. Most of it's the same, probably 70% the same. It's that extra 30% and then shoving it all in a year that makes it harder. Okay, visualize this. What I teach in AB is a semester of college calculus stretched out over about 7 months, and then I give you a 2-month review. What Helmers teaches in BC is 2 semesters of calculus shrunk in college, shrunk down to 7 months, which means you have to learn it faster than you do in college, and then have a 2-month review. So it's really probably harder than it is in college here. He probably does a better job because he's your friend and he teaches pretty well and he actually gets the mind of a high school kid. But you actually are learning it faster than you would in college. So you mull that over the next couple months before you register. But a good rule of thumb is if you can make an A in here, you're probably fine in BC. And then there's that question of, well, do I really even want to take BC if you're going to go into political science? Or if you're going to be like, my daughter took BC, but she's an architecture student. They don't even need Cal 1. They just need a math class. So why she took it, I have no idea, because she would have like spend these 9-hour study sessions. So I don't know why she did. Maybe she was sick of having her dad teach her, but she took it. But my son took it. It made great sense. He was an actuarial student, so he had tons of math. So knocking out a couple of semesters was great for him. But anyway, I'll be happy to talk with you individually later on about all that. But this topic we're doing today is covered in BC Cal. It's not covered in AB. So if you're one of those who's like, yeah, I'm going to take AB, and then I really won't need to take a math class, I'll pass the test, which most of my students do. The only math teamers that don't pass the AP exam are ones that literally do nothing. And that's rare. Even some of the ones who do nothing for me in AP pass. And sometimes they pass with 5s. But anyway, what this process is called is partial fraction decomposition. So when you're in calculus, calculus is based on rates of change. The whole idea is based on the concept of slopes of curves, okay? And to take a slope of a curve, you do what we call a derivative. You will take derivatives this year. If you are anybody in physics, nobody's in physics 2, right? Or C. Okay, so in physics 2 or C, you actually start learning derivatives and integration. Well, a derivative finds a slope. An antiderivative or an integral gets you back from your slope equation back to your original equation. And there's tons of applications of this. Well, in the process of integrating, an integral looks looks something like this. You're going to have some function right here. Okay. Well, in Cal 1, we learn all kinds of rules for finding integrals, right? But we don't learn all. In Cal 2, you learn more processes, or in BC, you learn even more process to do integration, but you still don't learn all. There's Cal 3, and there's a lot of math even beyond that, because some of these functions are really difficult to integrate. And one of the things that you run into a lot of time are fractions, okay? Now, fractions aren't that big of a deal, but you have a numerator and a denominator. And sometimes the way that that fraction is written is too ugly to integrate, okay? So in BC Cal, you learn this process called partial fraction decomposition, okay? And basically what we learn to do in partial fraction decomposition is take this big fraction and break it up into a bunch of smaller, tinier fractions. And the tinier fractions, our hope is that we can actually integrate those because they're less complex and they fall under the rules that we need. Now, we're not going to do any integration in here, but we are going to learn this process of taking these uglier fractions and breaking them up into smaller fractions. Does that kind of make sense? Okay, so for example, I think it makes pretty good sense to you if I were to give you something like 2 over x minus 1 plus 3 over something like x minus 2. When I add these together after getting a common denominator, right, I'm going to have a new denominator if I add those that has an x minus 1 and an x minus 2 in it. Does that make sense? And the numerator will be some uglier number. So what we're going to be doing is taking stuff like this and breaking it up into its smaller fractions. Except we're going to know this part, and we're not going to know the 2 and the 3. So we're going to put stuff like an A there and a B there, and we're going to figure out what that A and that B is. So we're going to be rewriting these bigger, more complex fractions as easier looking fractions. We're going to determine what the A and the B value would be to make it true. And then our hope next year in BC is when somebody asks you to integrate this mess and you go, oh, I can't do it, you break it up into smaller fractions. And when you go to integrate, then you go, oh, I can do that. Okay? So that's our hope with partial fractional decomposition. All right? So I'm going to go through some of the kinds of situations that you'll run into, what your strategy is going to be to actually break these up. And most people do pretty well with this. the part that probably gets them in the most trouble is just the careless errors that tend to happen. So I'm going to start you off kind of basic, and then we'll go from there. So first situation I'm going to give you is number one, what do you do? These are the three things that you're going to be looking at when you look at these. So the first thing is I am going to divide if my fraction is improper. Okay? Now, what I mean by dividing if the fraction is improper is that when you look at the numerator and you look at your denominator, okay? If the degree of that, the degree of the numerator is greater than the degree of the denominator, then you're going to do long division or synthetic division, whatever is easiest for you. Remember, synthetic division you can only do if the denominator has a power of 1, so you're probably going to have bigger powers there, like squareds or whatever. But if that's a squared, for instance, and the top was a cubed, you're going to take that bottom part, you're going to divide long division, and you remember what happens when you divide with division? You get a bunch of whole numbers, like, and I call them whole numbers, they're not fractions, like maybe 4x squared and 3x and a constant. And then you get a single fraction at the very end. So you're always going to want to do that, and most of the problems we deal with are not going to be that way. But if your numerator is bigger, actually, or equal, bigger than or equal, you're going to, yeah, so make sure you remember that, bigger than or equal, you're going to do long division first, okay? And then the second thing you're going to do is you're going to factor the denominator. Factor the denominator as much as you possibly can using the factoring rules we have. We're not going to factor with imaginary. I think we've covered that this year. Maybe we haven't. I forget. But have we talked about factoring with rational numbers and irrational numbers and imaginary numbers? Okay, if we've done that, we're not going to do that. We're just going to kind of do algebra 2-like factor. Factor as much as you can without getting into i's and irrational stuff and junk like that. So we're going to factor the denominator as much as you possibly can. And then this part it's probably going to need more explanation. But then you're going to look at the kinds of factors you have. Like you might have a linear factor. Okay? You might have a quadratic factor. Okay? You could have a cubic factor. There's all kinds of factors that I might have in this denominator. If you happen to have one of these, if I ever have a linear factor in the denominator, okay, if I have that, I'm going to end up having a constant in the numerator. I'm going to explain all this with examples. It'll be much easier. If you ever have a quadratic factor in the denominator, I'm going to use a linear situation above it in the numerator. This will make sense in a second. If I have a cubic, I'm going to use a quadratic. So whatever power you end up seeing as I start this process of expanding and rewriting this expression with these denominators, these right here, these are going to be what I do with the numerator. And examples are the best way to really describe this. Okay? And there's one other thing I'm going to talk about. I guess maybe there is a number 4. Everybody got this? I'll put it over here. Okay. And so basically, like if I have something like for example, if I end up with something like a 3x minus 4 as a factor, when I start my expansion, because that's linear, I'm going to use a constant variable on the top. If I end up with something like, I don't know, 2x squared minus 5, see, that's linear, so that's a constant, okay? If this is quadratic, then I'm going to have a linear expression right here. And the way I would write a linear would be bx, say, plus c. I'm going to be using different variables. If I have something like a cubic, if it's a cubic on the bottom, then I'm going to end up with a quadratic on the top. And I would do something like dx squared plus EX plus F. Just making a little sense so far? Again, I'm going to show you this process through a bunch of examples today. That's all we're doing. Okay? So if you see when we start the process and you start rewriting based on your factoring of your denominator, and you're rewriting this as a bunch of smaller fractions, because you're trying to decompose this, you have to put variables up on the top that you're not going to know, that you're going to have to solve for in a second. So you're going to look at these factors. A lot of times the factors are linear. So you're putting an A over 1, a B over another, C over another. A lot of times that happens. But if it's quadratic, you have to write a linear expression. So just think like mx plus b. But I'm just going to start with A and just keep writing the variables until I can't reuse A there and A there because I don't know if they're going to do the same. And then if I end up with A cubic or whatever the degree is there, it's going to be one smaller bit. All right? And then the very last thing is, every now and then, when you're factoring, you get a linear squared. Okay? Now, a linear squared, I realize that if you look at a linear squared, that really is a quadratic, right? But if we see a linear squared term, okay, in our original problem, right? And I don't know what's going to be right here. Let me just say it was like 2x minus 1. If I saw that when I do the expansion, okay, if I have this factor here, I'm going to have to write it once with the power of 1, and then again with the power of 2. But I have to think in my head, wait a minute, this was a linear term, so I have a linear to the first, a linear to the second, so I'm going to put constants right here and right here. If this had been a linear cubed, then I would have had a linear to the first, a linear to the second, a linear to the third, and constants right here on all of them. So I've thrown a bunch in your face, and they're probably not the best notes on the planet, but I honestly do think the best way to do these is just to start the process and just show you some examples. So with all that in mind, still working on it? You got it? Okay. Oh. Got it? Okay. Let's just look at examples. So the question would be like, write out the partial fraction decomposition of, and let's just say I gave you 5x minus 10 over, and I'm going to go ahead and have these factored for you because I don't want you to factor them incorrectly, and then the whole problem is a disaster. So in real life, what would be happening here is you would have been integrating this, and you'd have gone, crap, I can't integrate that. But maybe I can break it up into two smaller fractions because there are two factors here, one to the first, one to the first. But both of them are linear, aren't they? That's at ax plus b or whatever, mx plus b. That's at ax plus b. So what I'm going to do is I'm going to write the first one with just the x plus 2 on the bottom, right? And because it's to the first power, I only need to write it once. If this had been an x plus 1 squared, then an x plus 2 squared, I would have written x plus 2 to the first, x plus 2 to the second. But because it's just the first, I only have to write it once. And because that is linear, what do I put on the top? I put a constant. And you can pick any letter you want. I always just start with it. Now, this is also linear, so I go plus, and I put the 2x minus 1 here. Now, because that's 2x minus 1 to the first, I only have to put it one time. But like if that was to the fourth power, I would have to have 2x minus 1 to the first, plus 2x minus 1 to the second, plus 2x minus 1 to the third, plus 2x minus 1 to the fourth. But I would still consider them all linear denominators. And if they're linear, even if they are linear squared, linear cubed, linear to the fourth. Are y'all seeing that? So if they're linear, you put a constant on the top. All right, so I will give you some problems where I say just write out the decomposition, don't solve for A and B. But we are going to solve for A and B on the ones we do today. Well, until I get really brutal. I'm not going to ever make you solve for one if you have like A, B, C, D, E, F, G, H, I. I mean, I'm not going to do that. It takes forever. That's not, you're going to end up having this massive system. So you may not remember this, but tell me if you do. Do you remember seeing a problem like this where it said find A and B that would make this identity true? Now you did it in Algebra 2. Now remember it? I'm hearing some no, some yes. Okay, well, it was early in the year, so it's been well over a year. But what you do here, you're basically saying, okay, this is an identity. This is a true statement. I want to find the A and the B value that would make the left side equal to the right side. Okay, for every real value of x other than maybe -2 and 1/2, which don't exist. So how would you do it? Well, first thing is, let's just get rid of these denominators. So if I multiplied through everything by an x plus 2, 2x minus 1, what happens here?
Denominator on the left goes away.
Okay, so if I x plus 2, 2x minus 1 there, and correct, x plus 2, 2x minus 1 here, right there, all of that cancels, and you end up with just a 5x minus 10 on the left. But when I multiply that in, both of these got to get distributed in, right? Here times this, what cancels? Just the x plus 2, leaving you a with the 2x minus 1. And then when you do this times this, just the 2x minus 1s cancel, leaving you b and the x plus 2. Now, I am at this point going to show you an easy way and a hard way. Now, the bottom line, what you do for all problems, if you don't want to take any shortcuts, is recognize that these two things have to be an identity. It has to be equal. So what that really means is anything that has an x over here would have to be equal to anything that has an x over here. So if I multiply all of this, and then anything that's a constant over here would have to be equal to anything that's a constant over here. And that makes sense if they have to be equal, right? So the hard way to do this is to literally distribute it all out and use that mentality. And by the way, sometimes you have to do it the hard way. You don't in this case, but I'll show you. So what I would do here is say, okay, if this is true, then that would have to be equal to the sum of those two things because they are the ones that have the x's in them. And I could come over here and say, all right, x equals 2ax plus bx. And then these constants would have to be equal to each other. And I know when you look at a and b, they look like variables, and they are temporarily, but they stand for constants. Okay? The x is something that literally is truly varying. So right here, I would say also the -10 would have to equal to the -a plus 2b. And then you'd say, well, if these are true for any value of x, couldn't I just divide these x's out? And what would you have staring you at this point? That's just a two-variable system. Now, this process is not that hard here because I know how to solve a two-variable system without too much trouble. I'd probably just pull out the elimination method. You could do substitution, whatever method you want. You can pull out Kramer's rule if you want to. But I know I can solve this. But you can imagine as my A and B grow to A, B, and C, or A, B, C, and D, or A, B, C, D, E, F, and G, these become really big systems. Okay? You really don't want to solve a 6-variable system, I'm guessing. So strategies to make your life a little easy and maybe solve for a couple of these variables before you do this are a great idea. So here's one of those things. I'm going to go and get rid of all of what I just put there. All right, so if this is true for all values of x that are defined, okay, right? Because we're trying to find where this matches this for any x. Then right here, couldn't I just pick an x and plug it in there? Like if you really think about it, a couple of seconds ago, I had written down 5x equals 2ax plus bx. Isn't me canceling out that x kind of the same thing as me saying let x equal 1? If I let x equal 1, don't I get 5 equals 2a plus b? Okay, so if it works for any value of x, then why don't I pick an x that's really helpful and plug it in right now? Anybody see an x that would be really helpful in the process of solving for a and b? -2. Now, why -2? Because if I let x, and again, I can let x be anything I want. If I let x be -2 in this equation, what happens to b? It's gone. And all my x's become constants, and the only variable left is the a. So I look up at these factors and I ask myself, is there a value I could plug in there to make my life easy? I call it a carefully chosen x. And sure enough, if x is -2, I get -10 minus 10 on the left. I get -4 minus 1 is -5a. And the beautiful part of that is I get b times 0, which goes away. Now, I know if you're looking at this going, but x can't be -2 because that would be undefined in the original problem. I realize that, but it works. Right? And technically, when I'm plugging it in, I'm not plugging it into an undefined situation because there is no denominator. So even though in real life, x could never be -2 in this problem, it works for us to figure out what a is. And now I have a. Now, at this point, if you want to, you could take this 4 and go and just plug it right in there. If you want, knock yourself out. But I could do the same process again to figure out a just like I did b. Okay? And if you want to plug a 4 in, you can. But if I pick a cleverly chosen or a carefully chosen x, a is going to go away anyway. So what would be another carefully chosen x? A half. That set equal to 0 gives me a half. If I let x be a half in here, I can plug a half in there, and I get 5 halves minus 20 halves is -15 halves. If I plug a half in there, I get a times 0. And again, I know that a is 4. If I had the 4 plugged in there, I would have 4 times 0. Either way, it's gone, right? And then I plug a half in there, and I get plus b times 2.5 or 5 halves. And at this point, like before, I am ready to go. I can multiply both sides by a 2 to get rid of the 2, divide by a 5, and I get b. And once I know my a and my b, I know my partial fraction decomposition. So what is this equal to? That was the question, right? It's equal to 4. That is equal to 4 over x plus 2 plus -3 over 2x minus 1. And had you been in BC Calculus or Cal 2 in college, and somebody said, hey, integrate this problem, this would be impossible to do like it is. But now that I have it broken up, this would be a simple natural log of the absolute value of x plus 2 problem and a natural log of the absolute value of the 2x minus 1. A really simple integral to be able to find. Although we're not going to put that integral sign there. We're going to stop here. And if you want to drop that negative, you can. I don't encourage it. When you have constants, it's not a big deal. But if that was linear on the top, to drop a negative, you'd have to factor it out. Why do that? So I always put a plus here and put a negative up top if it's negative. You just don't worry about trying to clean it up anymore. All right, so that's one example. Let's look at another one. What if I had this? This is probably one of the more missed questions on my test. So tell me what you see in the denominator right there. It's factored into 2 linears. Okay, biggest mistake I see right here is people go, all right, 2 linears. There's an x to the first. That's linear. So I only have to write an x once. There's an x plus squared up 2 to the first. So I write that once, and I put an a and I put a b on the top. And people do this, and they're going to miss. I'm going to slash dot you at best. Because what didn't I do? First rule, I didn't divide. Whenever the numerator has a bigger than or equal power than the denominator, you can see right now, if those are constants and I add these two together, I'm not going to end up with x cubed, am I? Something went wrong here. So whenever that power is bigger on the top, which it is, that's a 3, this would have been an x squared. Right? If I multiplied it out, I've got to do long division. And I'm not going to do division one at a time. I'm going to go ahead and multiply this back together. So this, don't make that mistake don't make that mistake. So I'm going to have to take this, which is really what? X squared plus 2x. I'm going to have to take the x squared plus 2x. I'm going to put plus 0 because there's no constant there. And I'm going to divide that into 4x cubed plus 9x squared minus 2x plus 6. And y'all remember on long division where if you're missing a term, you got to get a 0 in there holding the place? Okay, so here we go. That times what gives me 4x cubed? 4x. And then 4x times all of this gives me 4x cubed plus 8x squared. And then what do I gotta remember to do? Change my signs, right? So change the signs and combine. So that goes away, which it should have, and you end up with 1x squared there, and then I just drop down the next term. Technically, I could have put a 0 there, you're right. All right, and then when I combine it, I get this. Sorry about that. And then I drop down the 6. Okay? And then you repeat the process. And unlike in Algebra 2, where I give you these long division problems that require like 10 steps, and they're so tedious and awful, it's not really like that here. You might have to do a couple different steps to get your terms, but it's usually not that big a deal. And then that times what gives me this? 1. 1 times all of that. And then you come in here and change my signs, right? Cancels, negative 4x plus 6. So what I got when I divided was 4x plus 1 plus negative 4x plus 6 over the x and the x plus 2. Are y'all with me on this? So this initially gives me this, 4x plus 1 plus negative 4x plus 6 over the x and the x plus 2. I'm going to pause, and then I'm going to erase this because I need some room. Are y'all with me so far? Now, once I do this, these two things are easy. Non-fraction values that are just polynomial numbers, x squareds, whatever, it's a simple, what we call power rule. Really easy to integrate those. It's the fractions we give us trouble. So once we do the division, what I'm going to do is say, well,